Hello everyone again and welcome to my channel. In this video we'll look at the third system in quantum mechanics, which is the quantum mechanical harmonic oscillator. Now the harmonic oscillator is known to be a model for vibrations in diatomic molecules, and diatomic molecule in the sense that in between two atoms we have a bond in between them, and the bond usually exhibits vibration, and this vibration is actually a characteristic of harmonic oscillator. Now first let's all look at the differences between the particle in a box, which is represented as this diagram over here, and that of a harmonic oscillator. Now first of all, a particle in a box exhibits this particular diagram where we have this particular space where our potential energy equals 0, but the walls is having a potential energy which is infinity, where the wave function equals 0. However, this space, which is this particular box region here, has a specific wave function which we talked about in our previous video, which is a sine formula. And in this particular case, we have a kinetic energy present in here, where we take into consideration the movement of our particle either to the left or to the right between this particular boundary condition, where x is actually from 0 to L, or you can just say that 0 is less than x and x is less than L. Now in this particular case, this is representative of a particle in a box. Now the other case is different, where we are looking at a harmonic oscillator, where we have a curve which actually is a quadratic function, and in this quadratic function this actually expresses itself as half kx squared. Now take note that this is a Hooke's law formula, and this Hooke's law formula actually goes from negative infinity all the way to less than x and all the way to less than positive infinity as the domain in here. Now take also note that this actually is the potential energy of the system, and the potential energy which is now taken into consideration in here is included to the kinetic energy, which is the left and right movement of our particles taken into account, and also the potential energy which looks at the up and down movement of our particles, then makes us to actually reveal the Hamiltonian operator to be the sum of the kinetic energy operator and that of the potential energy operator. Now as a result of this sum over here, since we know our kinetic energy operator to be negative h bar all squared over 2m, and this is including our second derivative with respect to x, and our potential energy, which is what we have over here, which is half kx squared, then what we realize is that we generate our formula for our Hamiltonian, where this is our Schrödinger's equation, and the Schrödinger's equation here shows us that the sum of our kinetic energy, which is this over here, and that of our potential energy in here is equal to E. Now take note that for we to be able to find the energy in here, first of all we need to perform a specific process which is called the power series. Now the power series is actually applied into this particular equation in such a way that we move e to the other side and here becomes 0, and then we perform our power series where we make y to be the subject of the formula, and then we do various derivatives and making our natural frequency to be equal to this. Then we actually arrive at this formula over here. Now arriving at this formula over here makes us to actually see how we can actually solve for E. So by solving for E, which is our energy, then we're able to arrive at this particular formula over here. Now take note that this formula is actually the energy of our system, and the energy in here is noticed to be quantized. Now this quantized state is actually reflected as the energy of our harmonic oscillator state, where the energy levels are quantized after the Schrödinger equation is actually solved in here. Now take note that n starting from 0 all the way to 1 to 2 to 3, 4, 5 all the way to infinity, and this energy here is represented as this diagram, which is shown in here at the bottom, where we have our energy diagram going from 0 to 1, 2, 3, and in here we have our x, this is our y, which is equivalent to our potential. And if you're trying to put the E values, E to the 0 in here equals to half h. This other side are going to a higher energy level, which is E1, and you're going to 3 over 2, 5. Now take note in here that this particular level here is our 0 point energy, which is n equals to 0, and the space in between each energy levels are all equal, and this is actually equal to h bar times our natural frequency over here. So once you're able to do just that, then let's look at how we can be able to define various of our probability density in here, actually determined from our wave function. Now our wave function for the 0 energy in here is actually this. But then when you perform your first wave function, what we realize is that our first wave function actually starts off in this particular case, then approaches this region and comes down over there. Now going to the second one over here, what we realize is that first we have this, but then it comes down over here, then that being formed over there, and finally our wave function where n equals 3 is actually starting off from here, coming down, crossing here, coming down, and approaches over there. Now if we try to translate our wave function into our probability, which is the square of our wave function, what we realize is that this actually stays the same in this particular case. However, we have our reflection of our negative region into our positive region. So in this particular part, we have one node in the first part here, which is our first probability density, and the other side here we have two nodes where we are having this with a small one here, and then we have another big one in there, and finally our wave function 3 for our probability, we have 3 nodes over there. So all these here are now represented in our energy diagram over there, and that is about it for this particular video. Our next video we'll be able to explore a typical potential energy surface in diatomic molecules. And thanks again for following me through this particular topic. I truly appreciate it. I hope you're able to understand how we're able to actually understand the generation of our energies which is based on the power series. We can't actually go into details on power series because it's so long process in there. We have so many formulas to take into account. We can't go through it in this particular video. But then once you're able to generate that energy, our wave function in here can be used to actually determine our probability, and from our probability we can actually translate our probability into the energy diagram of particles that are distributed over various quantized states in there. All this and thanks for watching. Please hit the comment down below, let me hear your thoughts. Hit the like, share and subscribe. By that way I can talk to you all later. Be smart.